Irodov problem number 1.65. A plank of mass m1 with a bar of mass m2 placed on it lies on a smooth horizontal plane. A horizontal force growing with time t as f equals at is a constant is applied to the bar. Find how the acceleration of the plank w1 and of the bar w2 depends on t if the coefficient of friction between the plank and the bar is equal to k. Draw the approximate plots of these dependencies. Okay, this is a good problem. Let's draw the diagram first. So, this plank is accelerating with W1, let's say. This block, let's say that is accelerating with W2. Okay. So, there is some friction between M2 and M1, but M1 and the surface there is no friction. Okay. Before we apply any physics to this, let's just try to visualize this. If I pull that body, the force is applied on M2. Due to the friction, if the force is slowly increased, you can imagine that because of the friction, both of them will move together for a while. When the force is just little bit more than the static friction which was holding M2 on M1, if force is little bit more, then M2 will slide on M1 and both will have different accelerations. We will divide this into two cases. Case 1 is when the force is less than the friction between M1 and M2. Okay. So, case 1, F is less than the friction force between, let us say, M1 and M2. Let me represent that as friction between 1 and 2. Okay. So, in this case, both will have the same acceleration. So, let us consider M1 and M2 as one system. Okay. Now, if M1 and M2 is one system, one thing I want you to realize, there is still a friction force between M1 and M2. It is a static friction because M2 is not moving with respect to M1, but for the system M1 and M2, friction becomes an internal force. There will be some friction on M2, but because of Newton's third law, there will be equal and opposite friction on M1. So, that cancel out, it becomes an internal force. So, for the system M1 and M2, my free body diagram will be this: M1 plus M2G. This surface gives a normal reaction N on M1 and M2. There is this force F. Because M1 sits on a frictionless surface, there is no frictional force, and this system is moving with some acceleration W. So, in this case W is equal to W1 and W2. So, both W1 and W2 is equal to W. Okay. So, this is my situation. Case 2 is when this force is greater than or just equal to the friction force between 1 and 2. Okay. So, in that case what will happen is we will consider M1 and M2 as different systems and then analyze their motion. So, for M1 the free body diagram will be, so M1 is here, M1G. There is some normal reaction by this surface on M1. Now, because M1 also gives the normal reaction on M2, M2 will give a normal reaction back on M1, which will be equal to M2G. Okay. So, this M1G acts on M1, this M2G also acts on M1. This N, which is the normal reaction from the surface, is acting on M1. Remember, we are doing the free body diagram of M1, so we'll have to consider all the forces that are acting on M1. Now this F force works on M2. It is not acting on M1. However, there is one more force that will act on M1, which is what? So if I look at, for a moment, just this is incomplete, but for a moment, let's look at M2's free body diagram. So M2 is pulled by gravity, M2G. There is some normal reaction from this bar M1 on M2. N2 is the normal reaction. There is this force which is pulling M2, and this is the case when M2 is sliding on M1. Okay, it is sliding on M1. So there is relative motion of M2 with respect to M1 is to the left. So there the friction force will work opposite. Now this friction, M1 surface, the contact surface, gives on M2 Fr. Newton's law states, so if M1 exerts a force on M2, M2 will exert an equal and opposite force on M1. So that is the force that will also act on M1, equal and opposite. Okay. Now in this diagram there is another additional thing that is missing. And what is that? Because we are looking at this body M2, let's say we are saying it is accelerating with some acceleration W dashed with respect to M1. Now because we are analyzing this body on the reference frame of M1, W dashed is acceleration of M2 with respect to M1. M1 is itself accelerating, so it's a non-inertial frame. So if M1 is accelerating with W1 with respect to ground, then we must introduce a pseudo force which will be opposite in direction to W1. So the pseudo force that will act on M2 will be M2 W1. Now this is an inertial frame and we can apply Newton's equations of motion. Now for case 2 then, we have a complete picture of the free body diagram for M1 and M2. Okay. One other thing I would like to highlight here is this is accelerating, M1 is accelerating to the left with W1. Okay. Now if you have questions about the concept of pseudo force, I have a different video on the channel that you can look at and understand why we introduced the pseudo force for when we did the free body diagram of M2 in a non-inertial frame of reference with respect to M1. Okay. So now we have two cases. We can obviously evaluate W and W1 and W dash through this. So I also want to evaluate the boundary condition when case 1 flips to case 2, when M2 starts slipping on M1, and that we will also take into consideration and we'll solve that. Okay. In the meantime, let's jot down all our equations of motion. So in this one, normal reaction is equals to M1 plus M2G. There's nothing to write there. I will skip that. So force F is responsible for the system's acceleration. So M1 plus M2 W. Okay. So from here we can get, if we replace F as AT, M1 plus M2 W, or we get W as AT divided by M1 plus M2. Now from here we can write Fr, the friction force, is responsible for, this is M1's free body diagram, is responsible for M1's acceleration, so M1 W1. Okay. And N1 will be M1 plus M2G. I'm not writing that. From here, we have two things. Fr, the friction force, is equals to K N2. and N2 is equal to M2G, so K M2G. Okay, don't do the mistake of writing this friction force as Kn1. Between M1 and the surface there is no friction. This friction is actually acting here on top of the surface, and that friction you can only get from the interaction between M2 and M1, which we get from this free body diagram. Okay. Now the other thing that we can write is this force minus friction force minus M2W1 is responsible for M2's acceleration W dashed. Now this W dashed, remember, this is M2's acceleration in frame of reference of M1, reference with respect to M1. So if W2 is M2's acceleration with respect to ground, then we can write W2 is equal to W dashed plus W1. Okay, this is what we need to find, but we'll start with evaluating W dashed first. Okay, all right. So from here, let's write down a couple of things. We can write F minus K M2G minus M2W1 is equal to M2W dashed, or W dashed is equal to, let's replace F with AT minus K M2G minus M2W1 divided by M2. Okay. From here we get W1 equals Fr by M1. Fr is K M2G by M1. Now we can replace this W1 here. So this becomes AT minus K M2G minus M2W1 is K M2G by M1 divided by M2. I should put this equal sign right here in the middle. Now let's just also calculate. So before I calculate W2, I want to do one last thing, which is to find out this boundary condition when friction is just less than equal to the force. At what time? Let that time be T0. Okay. When W dashed is equal to 0, or just when W dashed is just greater than equal to 0, that's my time where T0, when that flip happens. So when will W dash be just greater than equal to 0? When this numerator is just greater than equal to 0. So we can write AT0, because that's the time when it is flipping, minus K M2G minus K M2 square G by M1 is equal to 0. Okay. So T0 becomes, let's say we take K M2G by A common. So 1 plus M2 by M1. Okay. So at T0, M2 just starts to slip on M1. Okay. Now let's just, for completion's sake, just complete the value of W2. W2 is W dashed by W1. Let me just use this formula. Okay. So W dashed is AT minus K M2G minus M2W1 divided by M2 plus W1. So M2 AT minus K M2G minus M2W1 plus m2 w1. So this and this we can cancel out. So w2 value becomes at minus k m2g divided by m2. So we got three results. During the time 0 to t0, both w1 and w2 have the same value here, and this is after time t0, w1 is this, and after time t0, w2 is this. Okay, so we got three results. Okay. Now the question also asks to plot the graph of the acceleration to time. So let's do that. So let's say this is my acceleration axis and this is my time axis. Okay. At time equals 0, w is 0, so the graph will start from here. Up until t naught, let's say t naught is here. This is a linear curve, so this will start rising like this. So this is the value of both w1 and w2, and this value will be k m2g by m1. So if you substitute t0 on this, you should get the same result. Okay. So after t0, w1's acceleration will be like this, straight line. So this is w1's curve. How about w2's curve? So w2's curve is same as this up until t0. So let me just overwrite this a little bit. It's the same curve. After time t0, w2's curve will be somewhat like this. Okay, so this is w2. Okay. So this is a good problem which illustrates few things. Number one, the concept of friction, static friction, and also it illustrates how to use the pseudo force when analyzing a body's motion with respect to a non-inertial frame. Okay, so hope that made sense, and see you in the next one.